Good morning, everyone. Welcome. My name is Nathan, and today's training is on why the battery management system matters and understanding the BMS functions of PHI and AmpliPHI and simplified batteries. This is a NABCEP certified training, and if you are here for those continuing education credits, welcome. Please stay through the end, and I will put my email up on the screen, and I'll ask that you send me an email. I'll check the attendance logs, and I'll get your certificates issued. So once again, welcome. My name is Nathan. I will point out as we get started here today that I'd like you to use the Q&A feature, and I will get to questions at the end. My colleague Daniel is not able to join me this morning, so I'll try to get to all the questions at the end. This is typically an hour-and-a-half long training on why the battery management system matters. And I'm going to talk about the functions of the BMS, why a BMS is integral to proper operation of batteries. And then I'll talk about the specifics of our BMS systems and our batteries and how we have some advantages in the way that we do things. And I'll talk about sizing batteries as well as integrating with charge controllers and inverters. So first off, I do want to point out that AmpliPHI Power that makes AmpliPHI batteries has been around for about 15 years. It's a California-based manufacturer, and it was bought by Briggs Stratton over a couple of years ago now. Briggs Stratton, you probably know the name, has been an engine manufacturer for 115 years, been manufacturing generators for many years now. And so we're one of two companies in the US that manufactures both generators and now battery backup systems. So we've got a complete integrated energy solutions provider. Our products are engineered and assembled in the US. The batteries I'm going to be talking about today are manufactured just a couple hours south of me in California. And so we're happy to be able to provide a full scale of products, and so we encourage you to take a look into our product offerings. The batteries we're talking about today have a 15-year warranty on them, and this is a real true 15-year warranty on this AmpliPHI, SimpliPHI, this 4.9 kilowatt-hour battery that you see mounted on the wall in the background here. No throughput limitations. Unlike competitors, we are guaranteeing as many cycles as you like, full 15-year warranty on these products. So these are lithium iron phosphate batteries, and there are a lot of different types of lithium ion batteries. I'll talk just a little bit about that today, but we are using lithium iron phosphate, and AmpliPHI has been making lithium iron phosphate for over 14 years now, lithium iron phosphate batteries. And so we've got a lot of experience in this. We've got an expected cycle life of 10,000 cycles at 80% depth of discharge. And part of the reason for this large number of expected cycles has to do with the BMS. And so that's what we're going to get into today. We also guarantee 70% of the original capacity of the battery after 15 years. So we have an end-of-life capacity guarantee there. You probably all know, as you use a phone or use a laptop, it doesn't last quite as long as it used to after you've been using it for a number of years. And there is some degradation that happens inside battery cells with time, but with a good BMS, you can minimize this degradation. So I do want to point out, if you are a California-based installer, that you can get this self-generation incentive for these California manufactured batteries. And so the 4.9 should be on the list soon. The AmpliPHI and the PHI batteries are already on the list, so you can apply for a 20% credit if you're using a California-based manufacturer for generation incentive program out here. If you're not aware of this, right, the battery market is booming, it's growing, and we're expecting to see 33% of solar installations have battery backup by the year 2027. So 1 out of 3 installs, as opposed to what it has been traditionally, about 1 out of 10. And so as battery costs are coming down and as incentives become less and less to sell back to the grid, we're seeing a much larger, what we're calling an attachment rate, meaning attaching batteries to systems. So there are a lot of reasons for this market being driven. I'm not going to jump into all of them, but certainly EV adoption is going to accelerate this trend as well. More and more people are going to put a strain on the grid, and that will likely cause more blackouts. And we've seen blackouts being increased and brownouts increasing over the years. So AmpliPHI batteries, we've got a global footprint of over, in over 45 countries. Our batteries are distributed throughout the world, and we've got a lot of distributors out there selling these products. So depending on where you are, you might have a local representative that can provide batteries to you. To level set here in the beginning, I do want to talk about what batteries give you. So we all know that battery backup can give you the opportunity to back up in the event of a grid outage, but it can also give you the ability to do other things like shave peaks off your demand. So in other words, if you're getting these demand charges from your utilities for going over a certain number of kilowatts for your facility, then what you could do is supplement the power going to your loads with an inverter. So you could export some amount of energy to that loads panel when demand rises. And you do that by monitoring how much power is coming in using CTs, and then try to limit the power you're pulling from grid. Of course, you can also avoid time of use rates. I get pretty bad time of use rates out here in California, where in the evening time, they charge a lot more for the electricity. Now, my base rate out here in California, just signed up for a new plan for my shop. It's at 42 cents for part of the year, and then it goes up to 51, I think it was, during the summer. So, some of these time of use rates get pretty bad, and so you can avoid them by charging your batteries when electricity is cheap and then discharging them when it's more expensive. You do lose a little bit when you're using batteries. The round trip efficiency is not 100%, but it's pretty good. If you charge and discharge slowly, you can get 95% round trip efficiency with some of these systems. And then, of course, if you integrate renewables, most commonly solar, you can charge up during the day and then discharge at night when you need it. And this is what I do with my system in my home here. So let's jump into some of the basics. And I'm sorry, I'm going to take just a moment. I'm not able to see the Q&A right now, and so I'm going to have to exit my presentation here and see if I can get this Q&A to show up on my screen. I'm not able to do it. So I'm sorry, I'll have to try to jump to the Q&A here at the end. Let me jump into the basic concepts of an ESS, and we'll move through, and then I'll try to get to the questions at the end. My apologies. So what is an energy storage system? An energy storage system is really means a battery system in terms of homes, right? So a battery backup system, a way to store that energy. And we're doing that with lithium iron phosphate batteries now. There are other types of batteries that go on homes, NMC batteries, and I'll talk about the safety of different batteries. But it could incorporate many other things. Often, we're expecting to have monitoring and control, and that's important as well. We want to be able to see what our system is doing, what the status is. It could be attached to the grid, or it could be an off-grid system. And so attachment to the grid would be done through an inverter. And if you're attaching batteries and grid and solar, you're looking at a hybrid inverter, which has been the common way things are going, combining more and more components into a single inverter. So I'm showing on the left side of the screen a Solarc, looks like a 15K there. These are excellent systems for integrating many components, just like our generators. For instance, in the wintertime when less solar is available, and if you're in a place which gets frequent blackouts, you might want to have a generator there to be able to charge those batteries in the event that you can't do it from solar. And so one of the nice things about the Solarc inverters and the Briggs Stratton inverters is that they have a two-way start functionality built into them. They can automatically start up the generator when those batteries get low. and turn that generator on if the grid is unavailable to do that. So both inverters are capable of doing that. I want to level set again under just understanding key concepts, and I'm aware that most people that are going to be attending this webinar today will have an understanding of the difference between energy and power, but I'm going to point it out here anyway. Power is really how fast electrical energy is being consumed. So a common way of describing electricity and the consumption of electricity is talking about it as though it's water flowing through pipes. Power is how quickly that water is being used up, how quickly that water is flowing out of the tap into the bathtub or into any other electrical load that's consuming electrical power, right? Energy is a measure of how much. And I do really want to make that distinction. Even those of us that talk about this every day will sometimes mix up the units and say, how many kilowatts is your battery? Oftentimes, we're actually trying to refer to the capacity of the battery and mean to say kilowatt hours. So kilowatt hours is the unit that describes energy. And that's how much total energy you use over time. So you might use 30 kilowatt hours in a day, but at any given time, you might only be using a little over a kilowatt of power, right? And it adds up. So energy is power times time. Essentially, it's a little bit more complicated in that it's an integral because power is not a constant. But for the most part, power times time gives you the energy. You can see average power times time. To describe a battery backup system in ESS, I often use this analogy with water, and I wanted to point out, a good analogy for a battery is really kind of like an elevated water tank. The higher it is, the more pressure that's in those lines. That pressure in terms of batteries is a voltage, right? How much electrical potential energy there is there. And so I'm showing an installation that I had done in Ghana in 2019, where there's solar that's running a pump controller, which is pumping water from the lake up into this storage tank. And that energy is held there. I can discharge that tank to various parts of the village by just opening valves. And so the solar panels are essentially converting solar energy into gravitational potential energy for the water. Equivalently, a battery you get the solar panels converting solar energy into electrical potential energy, which can be later utilized to deliver that electrical energy to loads in the house. So again, that analogy here with power is how quickly the water is flowing. Energy is how much total energy you're being used, how much electrical energy did you consume over the day. So you can think of the energy as the amount of water that's in the tank. That would be the capacity of the tank. In terms of a battery, it'd be the number of kilowatt hours, the battery capacity. In terms of power, it's how much power the tank is capable of delivering, how quickly it's capable of delivering that water. So what a lot of people don't think about is the fact that batteries hold a certain amount of energy, but there's also limitations based on wiring, based on arrangements of the BMS, how quickly that energy can be delivered. So not all 10 kilowatt hour batteries are the same. Not all 20 kilowatt hours batteries are the same. Some might only be capable of delivering 5 kilowatts of power. Others, and I'll show you our 20 kilowatt hour stack here in a bit, are going to be able to deliver 14 kilowatts of power. And that all depends on the construction of the battery, the BMS, etc. So there are power and energy limitations on batteries. So don't just look at the battery size. So here's an install showing solar throughout the day. You're probably familiar with ratings of solar panels, and I can talk a little bit about that. It's something I've studied in depth. But I'm showing you as well, a lot of homeowners will think, well, I have an 8 kilowatt system. It will be will be producing 8 kilowatts of power at any given time when the sun is on it. Well, we all know that's not true. Right? The power output from a solar array depends on the angle of the sun. It depends on the temperature of those solar panels. It depends on whether or not there's any shading. And so I'm showing you an 8 kilowatt system in March, and it's peaking out at under 6 kilowatts just due to the angle of the sun in the sky, the temperature of the panels, etc. So with a fixed home solar power array, our goal, if we're adding batteries to that system is to overpower during the time when the sun is out. So this dotted line here would be to produce more energy during the day. And so if we look at power time on the horizontal axis, power times time would be area. So this area overproducing beyond our loads, which are red, the home is consuming what's red. If we overproduce, we can save up this extra energy here, put it in batteries, and use it maybe in the evening time or in the early morning time. And so the goal is to overproduce. Now, production varies throughout the year as well. So it's not always easy to size these systems. Often, if you're really trying to limit power from the grid, you want to size for the worst case scenario. And so in the Northern Hemisphere, that's when that sun is low in the sky during the winter months, like December, the end of December. So let's talk about the cells. And we're going to talk about the cells, the batteries, and what the BMS itself does. So we're using cylindrical lithium iron phosphate cells. There's a lot of different types of lithium batteries. Some of them are better than others for different things. Lithium iron phosphate, you get the longest number of cycle lives out of them. It's the safest battery chemistry that's out there. But cells like NMC cells are lighter weight. And so if you're building something like a drone, you want very high power output, very lightweight, and NMC might be a good option for that. LTO cells allow for very fast charge and discharge rates, but they're expensive and you got limited lifetime with those types of cells. So just keep in mind, we're using the safest, longest lasting battery chemistry for home battery backup because we don't really care about the weight too much. And we want long lasting, we want the most number of cycle lives, and we absolutely want safety. So inside the cells themselves, we're looking at some, sorry, I just got a message that you can now see my screen. I'm hoping that you could always see the screen. Inside the cells themselves, we have what are called cathodes and anodes. And I'm going to explain in brief detail how the lithium moves and the batteries themselves function. So first off, we have an aluminum foil layer on one side of a cell, and then we have a copper foil on the other side. The positive side is where that aluminum foil is. And what that is, what we do with that is we coat that with a metal oxide layer. And in our case, that metal oxide layer is iron phosphate, so lithium iron phosphate, so some lithium is embedded in there. And then it's separated by a separator layer. And then there's a graphite anode. The graphite is spray cast onto that copper foil, and what's in between all of these is an organic electrolyte salt solution. So organic electrolyte means that it's not water-based. And salt just means you have positive and negative ions there, which allow the ions to move. And the salt here is lithium, and the lithium is able to migrate between the metal oxide layer and the graphite cathode. So what charging up a battery does is it pulls the electrons off of the positive side and pushes them onto the negative side. That leaves behind positive lithium ions inside this metal oxide layer, and they're attracted to those electrons that have been pumped over to the anode. And so a charged battery is when the lithium has migrated from the metal oxide side to the graphite side to meet those electrons over there. To discharge the battery, we allow the electrons to run back through. We would replace the charger here with a load. We allow the electrons to run back through to the positive side of the battery. And the lithium, what drives those electrons is the lithium wants to be in the metal oxide layer. It's more stable in the metal oxide layer. And so there's this electrical potential which drives that reaction. That, in essence, is how a lithium battery functions. It's moving the lithium from a side it doesn't like to be in as much, the graphite side, to a side it likes to be in more, the metal oxide side. And a measure of how much it likes to be in the metal oxide as compared to the graphite side is the voltage difference of the cell. In the case of lithium iron phosphate, it's 3.2 volts. So what we have to make sure of, right, is that we charge and discharge these batteries in a method which preserves the energy, but does not create challenges. I'm showing here a picture of a Samsung Galaxy Note 7. This was the phone that was banned on flights because it could catch on fire. This is not an LFP cell, it's an NMC pouch cell. And I'm showing what can happen if you get some type of circuit failure. So if you get some type of circuit failure, you can actually get the lithium migrating directly between the cathode and anode in the case of a short circuit. And what that results in is a very rapid flow of ions, which produces a lot of heat inside the cell, which can even cause a fire in the case of the NMC cells that are shown here. So the job of the BMS is to keep the battery healthy and keep the battery safe. When a cell like an NMC cell goes into a runaway event in which the energy is being discharged and it's creating heat inside the cell, that can lead to the boiling of the electrolyte. And that electrolyte is something that has the consistency. Again, remember, it's an organic solvent. It can burn. And so if those gases that build up in the battery come out, you can get a combustion event. And this is what can happen. So just highlighting here, using an external party. I really like this channel, DIY Solar. This is Will Prowse, his channel. He took some NMC cells and LFP cells, some pouch cells here, and he drilled holes in these cells. And you can see the difference in the reactions. If you watch these videos, it took about 10 seconds for that NMC pouch cell to burst into flames, right? Whereas the LFP cell, he had to drill through it many times to even get it to off gas. And when it did off gas, it just released a small amount of smoke. It releases the energy much more slowly. And it just highlighted, and many of you have probably seen these nail puncture tests, etc. But if you get in an event where maybe a car bumps into the battery backup bank on the side of the house, you don't want it to immediately burst into flames. And this is one of the reasons that AmpliPHI had chosen LFP cells a decade and a half ago, right? They're safe. And even most of the industry, even Tesla, which has produced their power walls with NMC cells because they've been mass producing and using them for their cars, even their newest Powerwall, the Powerwall 3 that came out has switched over to LFP. So safety is very important, and that's one of the functions of the BMS is to keep the battery safe. One more point to make on thermal runaway events is when they do occur with NMC cells and NCO cells, different cobalt-based chemistries, is that the release of energy is a much faster release and they get to much higher overall temperatures. You also have to get an LFP cell to a higher overall temperature before you can even get it to go into thermal runaway. So all batteries are capable of thermal runaway if you get them hot enough, if they're inside an oven or if there's a fire in a house, etc. But LFP is much safer. It can withstand higher temperatures before thermal runaway begins. And then if it has begun, it reaches much lower overall temperatures than cobalt-based chemistries do. So let's talk about lithium iron phosphate batteries. Let's talk about what the BMS is going to do. So each individual LFP cell will have a nominal voltage. That means the voltage when it's half charged of 3.2 volts. So that's the middle voltage of a battery. When I charge a battery up, the voltage goes up a little bit, go up to about 3.5 volts. And when I fully discharge it, it'll go down a little bit, go down just under 3 volts. And so the job of the BMS is to manage those cells and to keep everything running. Now, inside the battery, to get to voltages of 48 volts, we need a string of 16 cells. So I'm showing on the screen just as an example, a 9-volt battery has a string of 6 1.5 volt cells in series to get to 9 volts. Well, the battery on the right side of the screen, a 48-volt battery, has a series of 16 cell packs to get up to 48 volts. So the job of the BMS is to maintain those cell packs, to keep things safe, to monitor temperature, and there are a number of different types of BMS systems. Communication-based systems have COM ports and allow the battery to talk to and and communicate with inverters, charge controllers, gateways, etc. So we'll talk a little bit about that. All of our batteries incorporate a DC breaker into them. This AmpliPHI battery's got a contactor inside there. And one of the things that the battery can do if there are unsafe conditions is to open up that contactor and prevent flow out of the battery. So a battery management system is the brain of a deep cycle lithium battery. It's what keeps it operating well. It manages and protects the battery from functioning outside of safe parameters, right? We want to maintain safe operating parameters. It can monitor various environmental and system-based conditions, such as voltage, cell temperature, amperage, the state of balance, the state of health, etc. It can provide programmable communications capabilities as well, and it can request different charge settings, different settings from the inverter, and it can control thermal management systems as well. In the case of NMC cells, some of these systems require external cooling systems. Most LFP batteries do not. But keep in mind, a BMS is not a valve that can, control the flow of current or a voltage regulator that can adjust voltage. It can't do those things. It can request that the other equipment adjust those things. So a charge controller or an inverter, those are the things which you can adjust the current flow or the voltage outputs on. The BMS does not have that capability. All it can do is tell the charge controller, tell the inverter what to do. Lead acid batteries, many of us are not familiar with BMS systems because lead acid batteries simply did not incorporate them. These are cheaper batteries that you would essentially get 2 volts per cell on, and they didn't really need battery management systems. The charge versus voltage curve on a lead acid battery is much steeper. You could essentially tell what the state of charge was entirely based on voltage, and you could just trigger your inverter system to react to those voltages. Well, the charge versus voltage curve for a lithium battery is much flatter, and additionally, we're discharging these lithium batteries in some cases down to 0%. On a deep cycle lead acid battery, you'd only really get about 40% usable amp hours in that battery. So the lithium batteries give us a lot better range, give us a lot better lifetimes, and give us a lot better functionality, but it does require some controls, and that's the BMS. There are different types of battery management systems. An analog BMS does not normally have a user interface. So the factory presets the equipment. Yes, you have integrated things like FETs to turn on and off current in event of protection events. But for the most part, you don't have programmability beyond what the factory sets in the beginning. They also don't really have the ability to transmit data to other system equipment like the inverter. A programmable digital BMS does. So a comms-based unit gives you the ability to change charge and discharge settings. It gives you the ability to see internal information. So I'm showing an example of a 16S 48 volt BMS that's there, and this one's from Overkill Solar. On the right side, you can see that there's a little Bluetooth dongle. All those wires hanging down in the center are what are called balance of system wires. So they balance cell voltages to make sure all 16 of those cells are at the same states of charge. It can take digital input and convert it into electrical signals to take access to take action. So this BMS is capable of being controlled. It's capable of outputting digital signals as well. Now, this is, of course, not the BMS that we use inside of our batteries. Ours is even more sophisticated. We've got a pretty advanced BMS that we've developed here in Oxnard, California. We program with firmware as well. So, but I wanted to show you that one as an example. So on low voltage systems, I can finally see the Q&A feed. So I'm sorry that I couldn't see it. I see there are a large number of you attending. Finally popped up on my screen. So how do you tell if a BMS is faulty, and do you have BMS replacement parts? Absolutely, we have BMS replacement parts, but we do those changes internally, in-house. We very rarely have a BMS go bad. And Bill asks, is there some way to do a health check on, say, your 3.8 simplified battery, maybe once a year? In fact, I was just doing this yesterday in one of my batteries. So there is a state of health information that the BMS outputs, and it tells you information about the overall capacity of the battery versus its original capacity. And so, yes, there are absolutely health checks that you can do. And one of the exciting things that AmpliPHI is doing now is going to be selling gateways with our Energy Track software that allows a high level of visibility into the batteries themselves. The BMS, a lot of these things are programmed into the BMS, and I'm going to talk about what are programmed into the BMS. But for instance, balancing of battery cells is done on charge cycles when those cells get a little bit over 54.4 volts, I believe is the threshold for balancing. So if you do have a lithium battery system, you want to make sure that occasionally you charge it to 100%. So you don't want to constantly be cycling the battery from 20 to 60% state of charge, 1,000 times in a row without getting it to a full charge occasionally. And that's a function of the BMS. The health of the battery does involve it getting to 100% state of charge or 99% of state of charge occasionally. And the way you do that is you follow the parameters, the programming parameters, if you're using an analog BMS, or if you have a communicating BMS like the AmpliPHI battery, the AmpliPHI battery will automatically send these programming settings to compatible equipment. Bill asks, so how does the installer do this health check? Well, you would need one of the gateways. So there are a couple of options for the gateways. So we do have a third party, New Sun Road, that sells battery monitoring gateways. There is a charge associated with this, and the charge, I believe, is $12 a month for battery monitoring with a New Sun Road gateway. And as I mentioned as well, Briggs has a gateway that we'll be offering that will have monitoring free of charge, but it will require an internet connection. How often does an installer need to do a health check, or how often does an installer do a health check? For the most part, with the communicating batteries, you really don't need to do a health check unless you're seeing some type of unusual behavior. However, if it was my system and if I was an installer, I would really want to check on my systems. If it's my system, I would check on it every few months, maybe once a quarter. If it's my friend's system, I would at least check on it once a year. And so I would recommend, if you've installed a number of systems in the past, to go out, turn all the batteries off, just leave one on, check the voltage of that battery. And if you have communications, you can monitor these things. Even like the Solar platform, for instance, gives information about the battery. So if you're consistently seeing one battery which has got different behavior than the other batteries, I would immediately initiate a health check on that one. And feel free to call our technical support team. You almost never wait on hold with us. You're talking to people with installer experience here in the US. And so if you do have questions about that, feel free to ask. So good questions, Bill. Thank you. And thank you, Fred. Let's jump through. I want to talk a little bit about our low voltage system. So typically low voltage system with NEC code refers to nominal systems 48 volts and below. Once you get into higher voltages, there are different NNC codes that apply. We do make high voltage stacks. So what I'm showing on the right side of the screen is a high voltage stack. These batteries are actually placed in series. I want to highlight the fact that we never place the low battery systems in series. The balance of system equipment that's inside that BMS does not function appropriately if the charge controller is running in series through batteries. So never place low voltage systems in series. They're always in parallel. And for the high voltage systems, these batteries come in either 24 or 48 volt options. We make both in Oxnard, and then they use what's called a stack controller. These batteries can go all the way up to 1200 volts with our stack controllers. and they have cell interfaces which monitor the health of the individual battery modules that are there. And these can get very large. These systems can be large. I'm showing just a single computer rack stack of the high voltage stuff, but you can do a whole container of these systems. So let's briefly, and I know you might not care about the details, but it is fun to kind of understand what's going on inside of BMS. So cell balancing is one of the primary important things to maintaining state of health of batteries. And I'm showing just a 4-cell system. So this would be a 12-volt LFP battery, but I want to talk to you about how this works. So passive cell balancing works by, if you're running a charge cycle and the cells inside the battery are in series, if you're running a charge cycle and current is flowing down from the top like this, if cell number 3, for instance, fills up before the other cells, it would prevent the other cells from filling up. And so what can happen is we can allow charge to continue to flow through cells 1 and 2, and then go around a resistor, avoiding cell 3, and then go down through to cell 4 and charge cell 4 by bypassing cell 3. Now, the downside to this is you're pushing that current through a resistor. Another thing that you can do is take that excess energy that is in cell 3 and bleed that off through that resistor. And this is always done at high states of charge. It's a little less efficient way to do it. And so I've got another question there on the high voltage stuff. But there is another method, and I'll show you another method. So Damon asks, did I say 1200 or 12,000 volts? 1,200 volts on the DC systems, Damon. So 1,200, it might be a little higher, but that limitation has to do with the battery management system, which we call the stack controller on the high voltage batteries that we make. Another way to balance cells, you can imagine if I have some type of power supply charging by having current flow down through the top on 2 different cells. And let's suppose battery number 1, cell number 1 gets full before cell number 2. Well, because they're in series, I wouldn't be able to charge cell number 2 up without passing that current through cell number 1, and I can't do that if the cell is full. So one of the things you can do is you can have active switches, digital switches, which are flipping between connecting a capacitor across cell number 1, and then they flip to the down position and connect that same capacitor to cell number 2. In that way, you can actively transfer energy or charges from cell number 1 through a capacitor circuit into cell number 2. And these switches flip back and forth very quickly. This is called active cell balancing, charge shuttling, and it's a much more efficient way to do this. So it usually occurs when the cells are almost fully charged. So it's at the top of the charge cycle. I don't know if other equipment providers do it on the bottom of the cycle. I think it's probably occasionally something that you'll do in very low states of charge as well. But this is usually done for larger scale systems, and it's a more efficient way to do it, which is why we use these types of features. Analog versus BMS, we do sell analog batteries. They do come in at a lower price point. And so it is important for analog-based systems that you have external equipment if you're going to be in situations in which the environmental conditions are bad for a battery. As an example, in very low temperature conditions, you would want, if you've got an analog system, you would want external monitoring, something that can shut off the charge controller equipment if you don't have a smart charge controller, things that can monitor temperature. So we do recommend the BMV712 battery management monitor or battery monitor from Victron. This is a nice monitor. I have one of these. Smart with Victron. Smart with Victron means that it's Bluetooth enabled. So you can get an app on your phone. I have the Victron app on my phone, and you can control all of their smart charge controllers, chargers with that app. I'm showing also the Connect SCP from Schneider there. There's external equipment you can get if you're expecting your system needs it. There are many cases where the batteries are housed indoors. The inverter itself can respond to temperatures, and you don't need extra equipment like this, which means you can go with a simple, more analog, cost economical system. Just a moment to connect with you on how to wire a system with closed loop communications. So when you do have closed loop communication, I'm showing our AmpliPHI battery here. With closed loop communications, you're going to what we call daisy chains. So we go battery 1 to battery 2, battery 2 to battery 3, battery 3 to battery 4, and then that fourth one you'll send a home run from what we call the device port to the inverter. So there are two ports that are together. These are for daisy chaining of batteries. The batteries talk to each other in a long chain. It's important to notice that when you get an AmpliPHI battery, it does come with what's called a terminating resistor, which is a little 120 ohm resistor that tells the BMS computer that, hey, this is the end of the CAN bus chain. And so you never want to have an open port on those battery device ports on a communicating battery. Ours or any other company's equipment, you always want to have a terminating resistor there. It says, hey, I'm the last battery in the chain. And so you notice that the batteries in the middle will always have both ports filled, but the battery on the end, you'll want terminating resistors there. And in our case, with our battery monitoring platform with our gateway, you would actually take one more connection from the last battery in the series, either on the left or the right, and run it into the gateway, and then you can monitor the battery. So either with our platform or using New Sunroad's platform with our batteries. So here it is all together, and the different, we've got two different battery sets bus together here, and you notice we're bridging that gap. So battery 1 to 2, 2 to 3, 3 across over here to 4, 4 to 5, 5 to 6, and then we're going to have a home run from the last one out to the inverter. There will be a terminating resistor here on the left, and there's a terminating resistor on this first one in the chain as well. The closed loop communications do allow the batteries themselves to tell the inverters, like a Solarc inverter or a Briggs Stratton inverter, what the settings should be. I'm going to take a second to check the questions here. Guess you might all be able to see the questions that are on my screen. Damon says, thanks. I was told it's not too good to have the batteries discharging at different rates. What scenario would cause different rates of cell discharge? So because the rates of the batteries, or the voltages of the batteries, will normally be the same, for the most part, batteries will charge and discharge at the same rates, with the exception that when you have batteries at different states of charge. So for instance, let's suppose you had one battery turned off and you charged up the other battery to full, and then you start a discharge cycle, you turn all the batteries on at once. You have one battery that's highly charged and the other batteries which are discharged. That highly charged battery will be covering most of the load, and it might even be charging your discharge batteries. So that's an example. Another example is where you're using too small of cabling between your batteries. And in that case, your middle batteries face a lower, support a lower fraction of the load than the end batteries do. And I'll talk a little bit about that with wiring of the battery cables, but that's hopefully an answer to your question. So thank you. Showing once again the high voltage, the stacks that are here, 200 to 1180 volts DC nominal. Keep in mind that that's not the max voltage. The max voltage will go up during a high state of charge. So this is that voltage at a 50% state of charge. Batteries are connected to a stack controller on the top, and that stack controller works with cell interfaces to monitor. In the case of our 24 volt systems, cell interfaces are not built in, and so we have cell interfaces that would be mounted here. And then the monitoring is done. We do use New Sunroad exclusively on our high voltage battery lineup. This is typically suitable for 3-phase stuff. So everything in the high voltage battery bank world is going to be either 208 3-phase or 480 3-phase. And I'm showing an Oztec inverter up there on the top, and then Solarc 30K system. And we're starting to sell a large number of these. 30Ks are becoming pretty popular as well. So just a little bit about battery specifications and C rates. Energy capacity of a battery, how much water is in the tank, how much energy in the terms of stored lithium can the battery hold. Energy capacity is specified in kilowatt hours. Current capacity is how much total charge that's stored there. And those two are fairly closely related. The amount of current that a battery will deliver is a somewhat fixed number. It's based on, it degrades a little bit with time as lithium might play out, but for the most part, the number of amp hours a battery has is fixed, at least at a maximum amount. The energy output of a battery varies slightly, and I'll talk to you a little bit about why, but for the most part, that's because under high rates of charge and discharge, a battery converts some of its energy into heat, and so it doesn't deliver as much of that energy output when you charge and discharge it quickly. Nominal voltage, that's the voltage that the battery is at when it's at a 50% state of charge. Another way to use the term nominal, nominal means named voltage, right? 48 volt systems, you know, a 48 volt system, that's the named voltage, but that's actually the voltage of a 48 volt lithium iron phosphate battery when it's fully discharged. C rate refers to how quickly you can charge and discharge a battery. And to try to make the C rate easy, a 1C battery is a battery that can charge or discharge in 1 hour. As I mentioned, there are limitations, especially how much current can run through a BMS, as to how quickly a battery can safely discharge. So a C rate of 1C, being able to charge and discharge a battery in an hour can mean very large currents running through that BMS. So to give you an idea, you know, when you're looking at a lithium iron phosphate 48 volt battery, it's about 50 volts. If I'm running 100 amps through it, which is what the breaker on our batteries are, that's 5,000 watts, right? So the batteries can generally surge at that rate, but you wouldn't want to do that full for 1-2 hours straight. So a battery that'll safely charge and discharge in 2 hours is rated at C/2. A battery that'll safely discharge in 3 hours, C/3. So the common numbers here are C/2, C/3, C/4, meaning the battery is rated for a maximum continuous charge and discharge rate of, you know, in as short as an hour, or in as short as 2 hours or 3 hours, C/2, C/3. Actually, the newest battery I'm going to show you at the end of this slide deck that we've come out with is a 1C battery, which means you could discharge it in an hour. So it's got a very high power output. Reduces the cycle life a little bit, but still very good battery that I'm very excited that we're releasing. So, all right, enough on the specs. If you have questions, feel free to ask them. It's important that, you know, as you're designing your system, to design it with the appropriate size, the appropriate scale, the appropriate voltage in mind. If you go to lower voltage batteries, and we do make 24 volt PHI batteries, that does mean that your cabling has to be that much bigger. If you half the voltage, you have to double the current. So do think about that as you're designing systems. And of course, when we get to very high power output and large systems, we go to high voltages because then we don't have to use massive 2-inch cables, right? You know, 350 kc mil and 500 kc mil. We can use smaller cabling if we go to high voltage, and that's a big reason that we do that. I'm not going to talk about the specs of this. I just want you to know, you know, for small systems, we make batteries as small as 730 kilowatt or 0.73 kilowatt hours, 730 watt hours. People typically will use these for tools. Miners will use these batteries for lights. And then people with mobile applications might use our 1.4 kilowatt hour batteries. These both come in 12 and 24 volts. We've moved away from those Anderson connectors you could see there and are using studs. This is a 3.85 battery. Nominal voltage is 51.2. This comes in either 24 volt or 48 volt variety. And if you half the voltage, then you've got twice as many cells in each cell block, and so you've got twice as much current. So 151 amp hours at 24 volts and 75 amp hours at 48 volts. The amount of energy this holds is 3.87 kilowatt hours. It's about an 86-pound battery. It's fairly heavy. This battery is the AmpliPHI battery, and the difference here is it's got the more sophisticated BMS, which will respond to high temperatures, low temperatures, give you state of health information, a lot of information through the CAN bus ports on it. This is, again, the same battery pack is inside there. We're using the same high-end cells in this battery, but you've got a more sophisticated communicating BMS. This is an outdoor rated 4.98 kilowatt hour battery, essentially a 5 kilowatt hour battery. It's rated at C/2, but it's also rated for outdoors. It's a waterproof battery. It can surge at 100 amps. If produced, a single battery can output 4 kilowatts for 10 minutes, for up to 10 minutes. For outdoor systems, we have larger enclosures. We even have systems where we build the inverter in. So it's really kind of a plug and play solution. That Boss 12 cabinet in the middle, you're looking at, fairly large system, 45 kilowatt hours. It's, the equivalent of more than 3 power walls. And it comes in an outdoor rated NEMA 3R enclosure. And as I said, the access cabinets, we can essentially use the top half of that enclosure to mount an inverter. I did want to talk about this just a little bit on the charge and discharge. It looks like my slide got a little messed up here. I'm sorry about that. But essentially what's shown is a voltage on the left, the vertical axis, and charging time on the horizontal axis. So batteries go through a charge and discharge cycle, which starts off at a constant current. And then that constant current causes the voltage of the battery to rise as the battery charges up. That's called the bulk cycle, the constant current cycle. We charge until we hit 56 volts maximum. And then we just maintain 56 volts at a constant voltage. And what happens is that the current was initially constant. And then when you hold it at 56 volts, as that battery goes from 95 to 100% state of charge, the current drops off slowly. And then you get a fully charged battery. So by the time you end the constant current bulk section of the charge, you're really at about 95% state of charge. And then for that last 0.1 hour or 6 minutes, that's the constant voltage section. And that's where a lot of that balancing occurs. So do keep that in mind, that you do want to go through the occasional absorbed cycle. The ratings are here. I'm going to send this slide deck. I want to jump into some newer slides. But I do want to point something out on the battery state of charge and voltage, because this is something that often gets confused. You'll see a voltage on your inverter that says 55 volts. Well, the batteries, when they're at 100% state of charge and just resting, are going to be at a voltage of around 53.5 volts, depending on the temperature slightly. So why would you be seeing a higher voltage on your inverter or your charge controller? Well, you must be in a charge cycle. And so what happens when when current is flowing out of a battery, as in the case of the blue arrow, there's a loss of voltage across the internal resistive parts of the battery. And when current is flowing into the battery, there's a gain in voltage across the internal resistance. So I might see the voltage of the cells plus something when I'm in a charge cycle. And if I'm in a discharge cycle, I'd see the voltage of the cells minus something. So let me illustrate that. This is resting voltage. You should see voltages at around 100% state of charge, starting at a little above 53 volts. And then it drops off fairly slowly until you get around to an 80 or 90% discharge, right? And then we hit what we call the knee here. It drops off really quickly out of that. We do recommend, if you're charging and discharging your batteries daily, to not drop below this part of the knee. So this is a resting battery curve. As I mentioned, during high loads, you do lose an amount of voltage across the battery. So if you set your low battery cutout to be at 50 volts, well, your battery could hit that 50 volts in a very rapid discharge. It could hit the 50 volts, even though the state of charge is fairly high. So what I'm showing here is a discharge example in which the battery voltage itself is 52.4 volts, which means the battery's at a 50% state of charge. But current is flowing out of the battery at a C/2 rate, meaning it would discharge the battery in 2 hours. So you've got about an hour's worth of capacity left. But as that current flows across the internal resistive parts inside the battery, we lose some voltage. So we're at a 50% state of charge. 52.4 volts is what we would see if there was no load. But under a loaded condition at a 50% state of charge at C/2, we have actually lost 1.2 volts there. And this is actually somewhat dependent on temperature. So I'm showing different load rates here. And as I load the battery and discharge it more and more quickly, right, you can see that those voltage curves shift downward. To get even more sophisticated, if I get the batteries really cold and I load them at C/2, it really shifts down. And so what I'm showing here, and I know I'm almost out of time, but what I'm showing here is these are some measurements I made at the university with a student that was working with me, and we're discharging these cells while the cells are in a cold oil bath. And so we chilled it all the way down, and you see the drop. This is resting voltage, is the dashed lines at the top under different temperatures. And these are C/2 discharge curves. So at about 40 degrees Celsius, there is a drop at 50% state of charge, about that 1.2 volts we just mentioned, right? But if I get that battery really cold and try to discharge it at C/2, so if I'm at 15 degrees Celsius, fairly cold, I'll see a slightly increased drop of another half a volt. But if I try to do this down at 0 degrees Celsius, I can lose 4 or 5 volts on a 48-volt battery. And so you'll hit low battery cutout much sooner when you're discharging a cold battery. The energy is still there. If you heat the battery back up, the state of charge is still there. But when you're cold, your batteries will cut out a bit sooner depending on your equipment. So I do want to point out another great feature of our battery. So one offering we have is we have this heating equipment that we can use if you're in cold locations to heat the batteries up when they get too cold. And we can integrate this directly into the BMS of our batteries, both our PHI and our AmpliPHI batteries that go in these outdoor cabinets. We can put these heaters in and integrate them, and they turn on and off depending on the internal temperature of the battery. So that's one option for cold weather. Of course, insulating your battery cabinet is an important factor as well. Charging and discharging temperatures, the range for our communicating batteries is actually extended. We can charge our batteries to very cold temperatures by charging them slowly. So the communicating batteries can control that charge controlling equipment and slow down the charge rate. So if I have a really cold battery, there's a lot of internal resistance. And what I can do is I can charge it very slowly at low temperatures, 1 amp, 3 amps per battery. And that will actually use the internal resistance to start to heat up the cells. And once the cells start to get warmer, we can speed up that charge rate. And this allows us to have a very large range of temperatures. When we get above 50 Celsius, around 150 Fahrenheit, we slow that charge rate down to 15. And above 70, it'll cut off to protect itself. So there's a pretty large range of temperatures we can go to in these cold environments. I'm going to skip ahead. I do want to show you something. We've got a new battery coming out, and they just started sales of this today. So pre-sales are happening. This battery is going to ship next month. This is our newest battery. It's stackable. And these stacks of 3 batteries, you can go up to 3 batteries on this. We can discharge these at 1C. So they're very high power output batteries. Each one of those batteries is 6.6 kilowatt hours. And you can do up to 6.65 kilowatt hours. You can do up to a stack of 3. So a single stack is 20 kilowatt hours. Again, even though we're looking at fast discharge cycles, we're still looking at over 6,000 cycles. So the reason there's a plus here is because, if we discharge it very rapidly at 0.75 C, meaning we discharge that battery in 1 hour and 20 minutes, we're expecting 6,000 cycles. Most customers are not going to discharge their battery really quickly every single time, right? They might do it occasionally. And so we expect that they'll probably get a lot more cycles than we get with the engineering lab, in which we're running it really fast. So these batteries can come in single stacks, double stacks, triple stacks. Each stack does have to have a stack controller on the top of it, and that's where the communicating equipment will be connected to go out to the inverter or the charge controller. The other thing I want to point out is that these are truly stackable batteries. The communications, all of the controlling equipment is there in those stacks. So the only wiring you have to do for this battery is the home run from the controller out to the inverter. A very simple option for us. These stacks, we can do up to 6 of these stacks in parallel, giving you a very large 120 kilowatt hour home battery backup system. And so we've specifically designed this stack to match up with a Solarc 15K. So a single one of these can meet the full power demands of the Solarc 15K. We've got a 20 kilowatt hour bank there. I point out that if you're doing large numbers of stacks, you'll want to use a DC combiner. And so I'm showing you some options here. Since I'm out of time, I'm going to skip. But for a Solarc 15K, the Solarc 15K has dual battery breakers built into it. And so you can do 2 stacks of 3 batteries, so a 40 kilowatt hour bank with a 15K without any external breakers or combiners needed. For a single stack, you'll want to combine those 2 battery positives and 2 battery negatives, and you can do that with these bus bars shown on the screen. We've got some packages coming out. Like I said, these packages were just released today, so if you're interested in the pricing, I'll show the numbers for the sales team and the application engineers here at the bottom of the hour. So I'm out of time. I do want to highlight, we have some promotions going along. And one of them is for our Elite Installer program. So if you're interested in becoming an Elite Installer, you've got some experience with batteries, we'll do a quick interview with you about your company. We'll verify that you're not a scammer, right? And we might get you on our Elite Installer list. One of the benefits is every battery you install for us, at the end of 4 months, we get you a $150 rebate per battery. So it's a pretty big rebate. Some of these checks can be pretty big to go out to our more prolific installers. So we've got some promotions running along. I'm sorry, the ones I was showing there are expired, but the 150 credit is still there. We still have that $1,000 promotion for your first system. And I hear there's even a promotion that's going to include a gateway. So if you're interested in joining this program, you can see all the installers that we have in this program so far. More to come. Thank you for being here. I will show the number in just a second, but those of you that are here for the NABCEP credits, please email me, energystoragetraining@basco.com, and I will issue that certificate. Do tell me how you want your name to appear on your NABCEP certificate. So I'll be sending this slide deck out to everyone. I'm going to check Q&A right now, and I'm just going to get that number on the screen there for if you're interested in a stackable battery. Does look like, so Bill says, is it a good test to turn off all batteries except for one and do a load test on each battery individually, checking voltage drop during test? Yeah, you can do that, which will tell you something about the internal resistance, Bill. We can even do a capacity test on each individual battery by running a load through it. You want to do this with specialized equipment. You can't really do that by running it through the inverter because there's some inefficiencies of the inverter. But running it through the inverter will give you a rough idea. And so, yes, it is. I would say, especially if you're testing your own banks or somebody else's banks, it's a good idea to occasionally run these tests and check on health. Damon says, how do we get the NABCEP credit? So thank you, Damon. One more time, we get the NABCEP credit by emailing energystoragetraining@basco.com. So energystoragetraining@basco.com. And if you're interested in the new battery, feel free to reach out to our application engineers. So once again, I'll send the slide deck out. I'll send an email out with your NABCEP certificates after I hear from you and how you want your name on them. And thank you for joining us today. Bye, everyone.